All right, let's talk about dynamics. Dynamics is the things or the reason why things move. This would be a study of Newton's laws. We just finished studying how things move. If you remember your kinematics, we can now predict and calculate where things will be, how fast they'll be moving, and under conditions of constant acceleration or zero acceleration. Now I want to figure out why things move. What are the causes of motion, and how can we calculate and understand these causes of motion? Things move, or better yet, change their current state of motion because of forces. We can consider a force to be a push or a pull or some form of contact that causes or has the potential to cause an object to change its current state of motion. Gravity is an exception. We'll talk about that later. So I want you to think about forces as push or pulls and touches. In order to exert a force, you got to be touching your object. How do you know if something exerted a force on it? Just like I said before, it must be touching it. If I touch something, I'm exerting a force on it. If I'm not touching it, then I can't exert a force on it. So we have to make sure we understand that. Note the words above. There's always going to be an agent of the force and a recipient of that force. Something always exerts a force on something else. That's going to be important. For example, if I'm on the ground, which is touching me, is exerting a force on me. In this case, the ground is the agent and I am the recipient. Let's talk about the one obvious exception to this rule. That would be gravity. Gravity is a force due to the interaction of masses with each other. We will talk about this in detail later. The gravitational force, though, can act without touching. Normally, gravity between typical objects is so small that we can ignore it. But because we live on a very, very large mass of the Earth, it's about 5.98 times 10 to the 24th kilograms, gravity does exert a non-zero measurable force on us. We call that force our weight. Fortunately, we have a very easy equation to describe our weight. If we are near the surface of the Earth, we'll use this equation. F sub g equal to W is equal to mg. I usually write forces as a capital F with a subscript, so the gravitational force would be F sub g, but we often use W as this interchangeably. In the above equation, make sure you realize the mass is in kilograms, not grams, and g is the acceleration due to gravity. Here on Earth, 10 meters per second squared. Let's look at the units of weight, and then therefore the units of all forces. The units of weight are kilograms meters per second squared. However, that combination happens so often we give it a special name. We say that a kilogram meter per second squared is a Newton, abbreviated by a capital N. Note that weight and mass are directly proportional to each other by the constant g. This is why we often refer to our mass in English units of pounds. But I want you to always use newtons as weight and kilograms as your mass. Weight is a force, and we will always use the metric unit of newtons as the proper unit. Your mass in kilograms is a measure of how much stuff you have, and later inertia, as we'll see, and we will measure that in kilograms. Also note that your mass is the same no matter where you are in the universe. But your weight does depend on the very large planetary body you're on. For example, g on the moon is about 1.67, g on Mars is about 4. So if I had a mass of 100 kilograms, my weight on Earth would be 1,000 newtons, my weight on the moon would be 167 newtons, and my weight on Mars would be 400 newtons. Now we can talk about Newton's laws. Let's start with Newton's first law, or N1. Newton's first law is really a statement of a law first theorized by Galileo. Galileo first discovered and theorized about the property of an object to keep doing what it's currently doing. Things that are not moving tend to want to stay that way. Similarly, things that are moving with a constant speed tend to want to keep moving with that constant speed. Lastly, things that are moving tend to want to keep moving in that straight path. Galileo called this property of an object to resist a change in motion its inertia. We measure an object's inertia by measuring its mass. Right now, for what we're doing right now, mass will be one way to determine an object's inertia. More mass, more inertia. More mass, more inertia means it's harder to change its state of motion. Newton restated Galileo's theory of inertia as his first law of motion. He did credit Galileo with it, but what he said, an object at rest stays at rest, or an object in motion in a straight line with a constant velocity stays in that motion, a straight line with a constant velocity, unless acted upon by an unbalanced external forces. What does this mean? Let's consider the two cases of N1. First, imagine a coffee cup on a table. It's not moving and it's at rest. That means all the force acting on it must add up to 0. In other words, there are no unbalanced external forces acting on it. There are forces acting on it. In fact, there are two forces acting on it. There is the table pushing up, it's touching the cup, and since the earth is near, there is gravity pulling it down. But these forces are balanced so the object does not move. If the situation changes, if nothing in the situation changes, the forces will remain balanced and the cup will remain at rest. It will remain that way until something happens, like me touching the cup. So, an hour from now, the cup will stay right where it is. A day from now, stay right where it is. However long, as nothing else changes, it will stay exactly the way. Here's the other part of N1. Let's consider the Voyager spacecraft. There it is. It's currently well past the Pluto orbit. It's moving at about 17 kilometers per second. It's very, very far from the Sun or Earth or any other planets, so there's really essentially no force acting on it at all. If nothing touches it or gravitationally affects it, it will continue to move at that 17 kilometers per second in the direction it's currently traveling. It needs no force to keep it going. It just wants to keep moving in its current state of motion. This is a little bit more difficult conceptually to understand than being at rest. But if you think about it, rest is just a special case of a constant velocity. In this case, a velocity of 0 meters per second. So what happens if N1 is not true? If there are unbalanced external forces acting on the object, that object will not maintain its current state of motion. It will either speed up or slow down or change direction. You should be familiar with those terms. Speeding up and slowing down, those are all accelerations that we've talked about before. And it turns out that changing direction is also an acceleration. As I said, changing objects can also be an acceleration. Fortunately, Newton mathematically developed an equation to describe how these unbalanced forces induce an acceleration. It's Newton's second law, or N2. It is arguably one of the most famous equations in all of science. And there it is. Sum of the forces, that's what that funny kind of E-shaped symbol on the left-hand side means. Add up all the forces. If those forces are not balanced, if there's something left over, that net unbalanced force will equal mass times acceleration. The right side is always the same. It's always ma. Unbalanced external forces always produce an acceleration. It'll be directly proportional to the mass, that's what they call the inertia, and it will be in the direction that the forces are being applied. The left side is where all the physics is. Once we identify all the forces acting, the left side is the unbalanced part that is left over. If it's not 0, N2 applies and we get an acceleration. If it is 0, well then we just go right back to N1. My object will maintain its current state of motion. We'll discuss a procedure to handle this equation soon because it is kind of complicated. It's not horribly complicated, but does require some care and some thought and some mathematical skill. On to Newton's third law, or N3. N3 will describe the relationship between the agent and recipient of a force. It is conceptual in nature and, as usual, takes a little bit of care and thought to understand it. Here's my silly famous drawing. I've got pairs. Inside those pairs are forces. Newton's third law says forces come in pairs. They come in pairs, P-A-I-R-S, not pairs, P-E-A-R-S. This is, I think, one of the clearest and simplest statements of N3. If I exert a force on you, you're exerting a force back on me. It's going to be equal, just in the opposite direction. After all, if you think about it, it's the same force, just changing who is the agent and who is the recipient. It has to be the same. It is important to be able to determine the agent and the recipient. That way, we can easily identify the N3 paired forces in a system. It does get confusing because there are times when you'll have forces adding up to 0, but they're not necessarily paired forces. Paired forces never act on the same object. That means they can't be acting on each other. Let's try a conceptual example. Back to my coffee cup sitting on the table. I'll begin to investigate the procedure I'd like you to follow. So first of all, I'm going to draw a picture. There's my coffee cup sitting on the table. Secondly, I'm going to identify all the forces. In this case, there's 2 of them. There's the table pushing on the cup. That's that one. And then there's gravity pulling it down. Third, I'm going to define a coordinate system. This allows me to discuss all the relevant directions and to make some math. I usually just make an XY coordinate system where my arrows point in our traditional X or Y directions. I'll get to step 4 and 5 soon. This is enough for right now. Now let's look at the force of the table pushing on the cup. Anytime you're on a surface, that surface is going to exert a force that is perpendicular to the surface. Another word for perpendicular is normal. So we call the contact force, when you're on the surface of an object, the normal force. It will always act perpendicular to the surface. The normal force can also be expressed as the force of the cup on the table. Here the table is the agent of the force and the cup is the recipient of the force. If I change the order of the words, I get the Newton's third law paired force. In this case, it would be the force that the cup exerts on the table. The table pushes the cup up, the cup pushes the table down. Let's continue with my example from the previous slide. How about gravitational force? What's the paired force for that one? The agent of that force is Earth's very large mass, and the recipient of that force is the cup. Earth's mass wants to pull the cup down towards the center of the Earth. The N3 paired force to that is the cup's very small, relatively speaking, mass, and the recipient of that would be the Earth. Not only does the Earth pull the cup down, but the cup is pulling the Earth up. Note in our example, the N3 paired forces do not act on the same object. There were 2 forces on the cup, 1 force on the table, and 1 force on the Earth. Our object of interest is the cup, so we're only interested in those 2 forces acting on the cup. Let's try and enter an example involving both N2 and N3. So, consider a truck of mass 10,000 kilograms going down the highway at a constant velocity. It's going to collide with a bug of mass 0.001 kilograms. And let's say, for purposes of argument, that the truck will exert a 10 Newton force on the bug. Here's my truck. Here's my bug that is clearly not drawn to scale. How much force does the bug exert back on the truck? Well, according to N3, they are paired forces. So the bug must exert 10 newtons of force back on the truck, just in the opposite direction. So the force that the bug and the truck exert on each other is the same. That's just Newton's third law. How about accelerations? Well, we can use Newton's second law to figure that out. Let's find the acceleration of the truck. According to N2, I get 10 newtons is equal to 10,000 kilograms times A. Solving for A gives an acceleration of 0.001 meters per second squared. That's a negative acceleration because it's going to cause the truck to slow down, but that's so small it's not even measurable during the time that the bug and the truck are colliding. So we don't perceptively feel the truck ever slow down when it hits a bug, which is a good thing. What about the acceleration of the bug? According to this, I would get 10 newtons is equal to 0.001 A. Now my acceleration is 10,000 meters per second squared. That's approximately 1,000 Gs. In other words, it'd be like having 1,000 of you sitting on your shoulders while you're standing up. That acceleration would be lethal to the bug. It turns into a jelly streak on the windshield. So the forces are the same, but accelerations can be much, much different. So, just to recap Newton's 3 laws. N1 describes what happens when a balanced external force acts on an object. The object will maintain its current state of motion. It'll either maintain at rest or it will move in a straight line with a constant velocity. In other words, the acceleration is 0. N2 tells me mathematically what happens if I do have unbalanced external forces. The object will speed up, slow down, and or change direction. According to Newton's second law, Sum of the forces equals ma. In this case, my accelerations are not zero. N3 talks about the fact that forces have to come in pairs. Forces have agents and recipients. The agent on one thing is a recipient of the paired force back. The N3 paired forces are just changing the role of the agent and recipient. Forces are equal and opposite, but accelerations are hugely different.